Hello, everyone. Welcome to today's technical webinar. This is part two of our two-part webinar series on game-changing new tech to help us understand and develop unconventional reservoirs. Last week's session, for those of you who tuned in, got a good taste of some new drilling and completions tech that's out there. Today, we're focusing on production, reserves, and reservoir aspects to some new tech and techniques that are out there. I'm really proud about today's lineup. These are all good contacts of ours that I've known for, in some cases, several years, in other cases, a little shorter time. But I think you'll really be impressed with what you're going to see today. Today's a 2-hour program. I just want to start by saying the opinions and techniques and tech that's shown in today's webinar, do not necessarily reflect the opinions of SAGA Wisdom. What we're doing here today is to give entrepreneurs an opportunity to showcase some of their tech. We have looked at it, it's been vetted, and we think that you're going to get some value out of this. So with that being said, I think we'll start off with our first presenter. And our first presenter today is Dr. Nagoo from Nagoo Associates. Dr. Nagoo is the president of Nagoo Associates. He consults on production operations and artificial lift projects worldwide. He's a pioneer of wholly analytical multi-phase flow modeling, and he owns the world's largest database of published multi-phase flow data. He currently develops and licenses multi-phase flow and artificial lift software solutions for operators. He's got 23 years of combined research and industry experience in various reservoir and production engineering roles. And he's got a master's and a doctorate degree from Stanford and the University of Texas, respectively. So with that, Darcy, please play Dr. Nagoo's technical presentation. Texas,
and today I'd like to share some fairly deep insights into a topic I've been in love with for quite some time now, critical gas velocity, and focus on some key multi-phase flow concepts that I believe is missing in the current understanding of critical gas velocity modeling. Hence the title of what does it actually mean and why it's so important. I'd also like to thank SAGA Wisdom for selecting us as part of their game-changing tech. So for the first part of the talk, I'd like to focus on what are some common misconceptions about critical gas velocity. And then I'll transition into why, this improved understanding is important, and conceptualize and validate our understanding with some key experiments and field data validations. And then finally, I'd like to introduce you to the tool that does all of these calculations of multi-phase flow, these automated production calculations of multi-phase flow and critical gas velocity and so on, the MAPI tool, and why it's an exponential technology for providing new insights into production optimization workflows. So what I like to do is, I often like to step back and look at the prize of what we're trying to do here. And in production engineering, we think about this world in terms of the latitude and longitudes of pressure and flow rates. And what we're really after is trying to find out that pressure profile along the well, those individual multi-phase flow characteristics along the well. And particularly in unconventionals, we're interested in things like slugging and critical gas velocities and holdups and so on. But if you really think about what the pressure profile is in a well, it's nothing more than a representation of what you have in the well, the volume fractions of the phases. And all of your flow patterns are just different types of manifestations of what you have there. So the pressure behaviors is governed by the volume fractions, and the volume fractions and the individual phase velocities collectively, that relationship is what we call the well slip behaviors. And that's the key thing that's actually causing you to see the different types of flow behaviors in the well, whether it's a slug flow or an annular mist flow or so on. And that's what you see visually represented in your slip, in the types of slip that you have. Now, the problem is that there's a misunderstanding, in my view, of what's actually happening. In that, when we think about concurrent multi-phase flow, the gas is not actually removing the liquids. What's actually happening is that there's a constant slipping between the gas and the liquids to various degrees, which we call different flow patterns. And we call that hold up. The liquids will be held back due to that slippage in concurrent flow. But in countercurrent flow, when you have partial or full countercurrent flow, you have both slipping and liquids falling back downwards. And that's a key difference because you need to have a deep understanding of the two different types of wellbore slip behaviors, which is characterized by concurrent flow and countercurrent multiphase flow. And this is really where we must start to understand critical gas velocity, because you cannot really understand the concepts of liquids flow reversal without understanding the differences between concurrent and countercurrent multiphase flow. And there's a large bodies of literature of both, but we tend to see more of in the petroleum industry, the concurrent part. And this is what has always been missing before, and it's a key source of misunderstanding. So when we talk about concurrent multiphase flow, we're always talking about, whether it's concurrent or countercurrent, we're always talking about liquids accumulation. But in the case of concurrent multiphase flow, the liquids accumulate in all sections of your wells, and you have this phenomena of the liquids being held back due to the slippage. So you have liquids slipping but not falling, and you have both concurrent flow of positive liquids rate and a positive gas rate. And that's how you develop a holdup profile. But in countercurrent multiphase flow, you have a new phenomenon, because now you have accumulation due to liquids slipping, still hold up, still slipping, but now it's additionally falling. And now you're going to be building up a static gaseous liquids column at the bottom of the conduit. And that's really, the source of confusion, because the onset of liquids flow reversal, which is what we call the critical gas velocity, it's the start of this countercurrent multiphase flow process. And that's so you start with partial countercurrent multiphase flow, and you continue until you have full multiphase flow. And that's important because liquids hold up is not static to liquids accumulation. So now that we understand that, we can finally come to an accurate definition of critical gas velocity, which is a gas velocity at which any part of your liquids flow field starts to reverse direction and fall downwards, not just recirculate, right? So we're talking about falling downwards. And it's a gas velocity at the onset of liquids flow reversal. But even that is open to interpretation, because what are you talking about? What do you mean any part? And if we start from a concurrent mist flow and we start decreasing the gas rate, we're going to countercurrent multiphase flow in many different ways. And the question is, are we talking about a partial fall in droplet mists? Are we talking about partial fall in annular? Are we talking about a mixture between? And the answer is the critical gas velocity is all of the above. It's a range. It's contrary to popular belief, it's not a departure, but it's a range. It's a point. It's a wide range. It includes all of the starting options for countercurrent flow. And the critical gas velocity depends on your different types of wells that you have. So, for example, a high GLR mist flow well will flow in this regime, but a liquids-rich gas condensate would flow in a partial churn annular flow regime. And the critical gas velocity is the onset, that point, just before you transition to your zero cross-section average net liquid velocity, and then your liquids start to have a net zero velocity. A net negative velocity. And all of this happens in multiple ways across a wide range of different transitional flow patterns. And that's important because now we can finally understand why we have slow liquid loading in some wells, and why we have sudden liquid loading, fast liquid loading in other wells. And that means we're accounting for the full range of liquids loaded. And that's an important term, because that's an important differentiation into what we understand by liquids loaded. So it's not just about, what happens here, like a tinner analysis, or what happens individually here, like in a film analysis, but it's the full range of this wellbore behavior. And, it's a very involved topic, so this chart here describes the countercurrent multiphase flow process as you start from mist flow all the way down to your transitional flow patterns that you saw before, then to slug and to countercurrent bubbly and so on. And then your wells, there's a whole concurrent multiphase flow part. This is what you normally see in your flow pattern maps and so on. And your wells, flow in both regimes at different times along the well life, and individually along the same well. The difference in the understanding that I created in the critical gas velocity model that I have is that we're able to combine that full range. We're able to capture that full range and look at the upper asymptote of liquids loading and the lower asymptote and combine them. So now that you understand what is liquid loading, now you can clearly say what it is not. So it's not the onset of flooding. It's not the liquids droplet only. It's not the liquids film only. And it has nothing to do with the change in pressure gradient curve or or liquids accumulation and so on. Because once you have accumulation, you're already past the liquids loading point. So now that we understand what liquids loading is and the onset of flow reversal and countercurrent multiphase flow, now, that calculation, and if you can get that calculation, how do we conceptualize that understanding into a method, a calculation? And that calculation is very important. It's one of the most important calculations if you're talking about the eventual removal of all of the liquids in your well, which is what the definition of artificial lift is. And I've been using this new understanding in my critical gas velocity equation, called the Nagoo equation, in many different ways. I have a new methods coming out for a virtual wellbore liquids meter that uses this calculation, a real-time plunger rise velocity tracking algorithm, slugging detector for automated gas lift, and so on. But the most important application that we should care about and that we need to get right, the holy grail, is if we can predict early liquids loading detection and diagnosis. And cost effectively managing your wells means that you want optimize remediation and intervention responses in response to better quality and timeliness of liquid loading prediction. So the prediction needs to come before the remediation, not the other way around, which is where we currently are in terms of our understanding. And I could give you, different figures, broad figures. About 95% of your wells will need artificial lift, or 90% of your wells are liquid loading. But the figure that really matters is this figure here, which is only 20% of your potential well life is going to be freely flowing, and the majority of your well life, you're going to need to understand when and where you need to apply artificial lift. And it's a deferred production that's the most costly part of your wells. And if you get this right, if you don't get this right, there's a lot of problems. You might not be in business that long. Your investability equation might change, and you might have reserves right down. And it's something to get right because, we don't only want an analytical, explainable, simple, first principle derived model, but more importantly, we want an inclination and diameter dependent model, and we want a liquids loading calculation that predicts early liquids loading that includes the full range of liquid loading. And those things are particularly important for unconventional wells. And that brings me to this equation, which is the key new equation that I came up with, and I and many others. It's a collaborative study, SP 190921, and it's the industry's first full range liquids loading model, and to my understanding, the only full range liquid loading model that has explicit dependencies on the diameter and inclination. And it turns out that diameter is the strongest effect. And it's well validated against many shale unconventional reservoirs. And when we talk about full range, again, just a reminder, we're talking about all of this partial countercurrent flow, that onset of flow reversal. So, and that's very important to remember because any amount of liquids will load a well, not just it's not just a lot of liquids or a little bit of liquids. And if we have that understanding, now we get that same equation is this red line here. And, if you compare that with your gas well, velocity, you can see, you can begin to use this simple analysis of these two different profiles to find out a lot of things that's going on in your well. So for example, you now have a technical, quantifiable, explicit calculation of where your energy bin should be from a technical standpoint, not necessarily from an operational standpoint. And you begin to see which different parts of your well has liquids loading and that complex interaction between the fluid dynamics around the bend and so on. And it's not just individually within the well. You can use this critical gas velocity and well gas velocity and plot it for the life of well. So you can look at your life of well liquids loading and calculate precisely on a lift curve where you have your onset of liquids loading, and therefore you can now quantify the lost liquids production and gas production that you can get if a well were to load. And this is a huge advancement beyond Turner and Coleman because, as you know, Turner and Coleman has zero diameter effect and inclination dependence in critical gas velocity equation. But what we typically see is the critical rate equation, which is the PVT conversion of that, and we sometimes get confused with those two things. So what's the best way to test our understanding, or improve understanding, is to look at very simple cases both field cases and lab cases of observed onset of flow reversal, right? And here's a Texas Tech experiment where you have, a comparison between the Nagoo equation, the Turner equation, and Coleman equation for a large number of experiments done by Jim Lee and others. And you can clearly see a drastic improvement. Here's a University of Tulsa experiment where the gas velocity was systematically reduced until the liquid loading was observed. And if you didn't have the Nagoo equation, which is the red line, to correctly capture the liquid loaded observation, you would still be above the Turner line and so on. And then not just experiments, it's in real wells. Here's a real well profile. And what we expect is that in some cases, for example, in smaller diameters, you can just coincidentally have the Nagoo equation and Turner equation coinciding. It's not much different. This is 1,000. This is, and 1,400. Coleman will always be less. But the real value comes in when you can see significant differences. For example, this is a SPE dataset that they recently released. And you can clearly see, there's a huge difference in the Nagoo equation and Turner and Coleman equations. And you can capture that very precisely. So you can finally forecast critical gas velocity and onset of flow reversal. And it's not just, US wells as well. There's a lot of different papers, different types of diameters, sometimes large, very large diameters that you can, finally get this thing correct in terms of the actual observed loading. And, there's a continuing effort. This is an independent validation of the Nagoo equation, in an Aramco paper. And, just to keep in mind, there's also the annulus multiphase flows as well, types of validation. So beyond prediction, there's diagnostics, so you can diagnose what's going on downhole, and you can see the differences between slight loading and severe loading. In terms of remediation, you can apply gas lift. So in this particular Eagleford three-phase gas condensate well, water well, the gas lift, when applied, didn't really solve the liquid loading and the lateral loading. And of course, there's the tubing calculations that you can make as well, and you can find out precisely at what angle your different critical gas velocity would matter. My final portion of the presentation is to introduce you to MAPI. MAPI stands for Multiphase Analytical Prediction Engine. It's the V7, it's the newest version. There's a lot of things that's changed. In case you missed it, there's now the possibility to run thousands of wells, all of these different wellbore simulations very quickly. MAPI is all about 80-20% workflow optimization. So we used to live in the world where simple correlations or niche calculations was important, but now we live in a different world where the technology is only a part of the bigger picture, and automation and the time gains from workflow optimization really matters, and that's why you need analytical tools. And automation means democratization as well. So the difference between MAPI and other codes, it's the VBA code is all open. It's a huge head start. So you can think about it as a Raspberry Pi of production software. It's a canvas. And what I'm focusing on my time on these days is just making a lot of MAPI YouTube videos showing how to use these automated calculations. So it's important to keep in mind that yes, you can solve everything, throw the kitchen sink at everything, and take a bunch of different wellbore models and combine it together. But the real value, but if you don't understand what's going on a well by well basis, combining those things doesn't really add value. You actually decrease value. So MAPI's disruptive mission is to improve and optimize and automate those production workflows at the well level. And the improvement comes both from the fundamental deterministic theory, as well as, in many cases, MAPI's technology far exceeds what you have in the industry right now for individual things. It would be remiss of me to say that, MAPI's also has a lot of unique things that are based. It's also based on also has the world's largest validation database. So it's many individual things and incredible things all coming together to make a disruptive advancement in analytical automation friendly production workflows. And that's that in combination with a much better understanding of critical gas velocity is how we're going to have a baseline understanding for science-driven production optimization. And with that, I'd like to say thank you, and I'll be happy to answer any questions.
All right. That was really terrific. Thank you. But we've got to clip along. So thank you very much, Dr. Nagoo. Real pleasure. I want to buy you a t-shirt, by the way, that says "Be better than Turner, be better than Coleman" on the back. So you're doing a great job. Appreciate it. Okay, Darcy, can you cue up the next one, please?
Hi, my name is Kevin McCormick, and I'm delighted to have this opportunity to tell you a bit about Petra Ninja. First off, thank you to the SAGA team for inviting me. It's quite an honor. Today, I'm not going to try and bore you to death with a list of features and data sets, but as background, Petra Ninja is a web-based technology with oil and gas data across Western Canada and into the United States. So you can get it at petraninja.com. You can see production, documents, and a fair bit of it you can actually view for free on the free version. Exports, filtering, lists is kind of where it turns into a paid account. But the larger vision of Petra Ninja is not that we can be another data provider, that we're going to kind of compete in that area, because there's an area of interest to me that's a little bit more personal and certainly a part of my experience when I worked in industry. So I used to work for a producer, and I started off in Medicine Hat, kind of in the field. I went to Calgary and got to see and work a lot more in the Western Canadian Sedimentary Basin and different roles like completions and facilities. But what was common in all of that is how much data wrangling there was for almost any task. So just a couple examples I'll go through. If I wanted to forecast a well, of course, I always need to go into my data application, my mapping tool, pick my well, export it, load it into my economics and forecasting system. And then that wasn't always synced in the future. So if I wanted to come back and do material balance or re-update my forecast, I had to usually go and get that same file, pick that same well again. Another example, if I was part of a, let's say, reactivation project, we're looking to reactivate a well, I might need like 10 or 11 applications open. I might need to talk to 4 or 5 other people because there's quite a few different disciplines involved. I might want to know what's downhole, what kind of tubing we had, if there's a pump, and where did we used to run it to what depth. Is it a JV well? Do we own it 100%, or is there a partner that I need approval from? What about the mineral rights? Are they due to expire soon? Is that a consideration? And then overall, like, is this project economic? Is it going to clear the hurdle rate? So I might have a relatively small project that involves me talking to quite a few people, me looking at quite a few different applications. And that's really kind of at the heart of where I see opportunity right now. Certainly, I think in all of North America, companies, the oil and gas companies, is starting to look a little bit different. When I was kind of in industry, there was quite a few engineers and there was quite a few office towers that were full in Calgary, and that's just not the case anymore. But the production really hasn't changed that much, especially here in the US. It's continued to be pretty strong. So there's a lot of kind of burden placed on engineers, on geologists, on the technical staff, and basically technology's got to make up the difference. Companies need to start to leverage their technology better so that they can grow without having to get back to the same size that they might have been, a decade ago or even a few years ago. So what I'm going to kind of talk about today are, 2 examples of these workflows where we can help a company handle some of this data wrangling problem. I think just pointing a little bit at kind of direction and the value we're trying to offer a business will provide you with kind of a good understanding of this product and our vision for the industry. Now, to start off, in Canada, one of the big areas of interest is the Montney Formation. So I can just type in under producing formation, the Montney. We're going to get a list of probably, I think, 14,000 or so wells. And those wells are going to show up on the map. But what do I know, being some, foolish engineer? frequently I'd always be working alongside a geologist to try, before I got too deep into well comparisons or asset evaluations, I'd kind of want to understand some of the geology. What we're working on is, how does that geologist work better with the engineer? Now, this product is a shared workspace at the enterprise level. So what that means is that the geologist and I can actually be on the same map. And further to that, the geologist can upload layers that I can see. So for example, one of the products we're integrating with is Sizeware, and they have a new geology module. One of the things that they did for this presentation is they took the Montney 3D model and they made some layers. Right now, we just upload them, but they're automating it so that soon you'll be able to push a button and push that layer to Petra Ninja for kind of a presentation view. So if we turn on, let's say, the Montney porosity, this is just in Alberta, but we can see kind of the wells on top of this layer that was built in Sizeware. We can play this with a couple of the other layers they prepared, but helpful for an engineer to kind of see where are these wells falling. And we could kind of further filter this. Like, let's say we're just wondering, where are the wells from 2018 being drilled? So 2018 to today, where are we seeing activity? We can see it's primarily on this fairway here. You don't see as many being drilled up here. Again, geologists are probably batting their heads against the wall at this dummy over here, but you get the idea. The geologist is adding data. The engineer is able to play with this. The land management is able to play with this and the wells on top without any complex queries, without anything difficult like that, but just to overlay them on the map. And the whole process is not any importing and exporting or anything like that. It's going to be a button you push that from Sizeware to Petra Ninja. You overlay this file privately to your account. Beyond that, like, I can add lists. Since we're on the shared workspace, the geologist and I, or the land person and I, or anybody else, operations, I can create a list of wells and save them to our shared account. So if I wanted to add this, I could say Montney wells or Montney activity since 2018, and give this a color. If I'd like to share this with our whole company, I just toggle this on and click create. And now the whole company, when they come to Petra Ninja, whether they're on their mobile device, whether they're on the web application, will be able to turn this on just by selecting this button here. So what we're highlighting there again is Sizeware talking to Petra Ninja, and what's that trying to solve? But how the geologist and the engineer work side by side, or how any two, people in the business who are trying to work with spatial data together can share files, share data in the same interface, so that you're not exporting pictures or Excel spreadsheets, or maybe we're not going to be able to sit around a table and look at a map as frequently as we used to if more and more teams are going to be remote. So this becomes, your digital table where you can layer over all kinds of different plans and data. So one of the other kind of examples, not only do we look to tie in software applications like Sizeware so that Sizeware is integrated, but other proprietary data sets. So our friends at Enlightened Geoscience were involved in a study, and I'll link to this study. And this is I think it was on the middle Montney, but this is a gas wetness. So the green is a bit wet, red, very dry. Again, all the details will be in that report I'll link to. But they were able to push this layer for us to add onto Petra Ninja. And now we can turn on, for instance, our layer that we just created of Montney wells drilled since 2018 and see where these are falling. And, big surprise, a lot of it's either in these oil portions or some of the wet. But if I clear all this, we can see as we zoom in, There has been typically a fair bit in the dry gas that was drilled. It's just not over the last 3 years. So that is an example of, here's a data provider that has data accessible to Petra Ninja as just a layer you can toggle on and off, so that you can kind of jumpstart your Montney project, your Montney understanding, by using other proprietary data sources without having to try and figure out, okay, I'm going to buy your Montney study, but how am I going to work with it? Is it just a PDF document, or, you know, how am I going to connect this back to the data of what is this well? How is it drilled? What do we know about it? All of those kind of, you know, so here we can find pressure data and well logs and gas analysis and everything else. So this was an example here of how we could turn on a layer that was provided by a third party, Enlighten, or I guess Enlighten was involved in this study. We also will help companies tie in their data sets. So if we take an example, or we look back at that example of poor old me trying to reactivate some old stripper oil well that was maybe pretty marginal, and needing to look at the accounting and project or do my forecast and understand the mineral rights and all that kind of thing. What we've done with quite a few of our customers is that we'll connect to their SCADA, or their daily production information, so that as you click on a well, your company will now be able to view whatever data you have there. If you connect your accounting information, you can kind of see what your net operating income is and what the fixed and variable costs for this well have been over the last couple of years, which is, I think, very valuable for field operations to understand where the money gets spent for these wells and to identify cost savings opportunities. Adding in land systems and a few other things like your DOIs, so that you know everything about this well and your well's on the map, right? You don't have to have 10 applications open up. But the final kind of data wrangling thing we're going to just talk about, and it's actually going to lead into the next presentation by Subsurface Dynamics, another company, separate company that's developing on the Petra Ninja platform, is how you can click a button and launch a tool. So the tool we're going to kind of focus in on today is this Subsurface Dynamics Athena, which allows you to forecast. So you can send a list of wells or a single well. But if I just select this well, so maybe we're looking at the production chart here, and we're wondering, okay, what is this well going to produce cumulatively, or, you know, what's the EUR? If I click the SSD button here, it's going to throw this out into a new window, a new application. It's going to generate the probabilistic forecast. I'll be able to play with it here. I'll be able to say, actually, that looks like a pretty decent forecast. But I could further, you know, change some of the different values here and enter in different economic variables. The whole point is that I didn't have to export and import. I didn't have to open another application. And I was able to do this all on the web with a push of a button. Subsurface Dynamics is going to actually take some of this data and launch I think kind of a bit of a study, a case study on how they can use this workflow to identify opportunities, and probably in this Montney area. But I just wanted to show this idea again of what we're trying to do is take away that friction, so that if I'm interested in this well, and I, for instance, might have geological data I can overlay to see, this is crossing a fault, it's part of the oil pool, the Gordondale oil field. I could click on the production and view all the public data, all of the well details from gas analysis and pressure. And I could also go to documents here and see, you know, we've got well test for pressure data, fluid analysis, directional surveys, logs. But if we have our own data, I could also view that. So maybe I could view today's production, today's pressure, And then I can click a button and start to look at what this well is going to generate the company in terms of cash flow and in terms of reserves, whether that's a single well or a group of wells. And I think that's the story we're trying to get at, is how can you give your technical team the tools and the workflows so that they can spend more of their time actually working with the data, like not on the data, but understanding, trying to gain new insights, make decisions, not all this time wrangling data and trying to move it around and bring, reach out to 10 different departments to understand what's going on here. And that, I think, is probably enough for right now, but I will thank you again for your attention. Thanks, SAGA, for inviting us. I'd be delighted to spend some more time with anybody who'd like to learn more about Petra Ninja, so please reach out. We can show you all of the different public data we have and some of the other features, as well as how we help companies work with data. And with that, I will take any questions.
Thanks a lot, Kevin. Our next presenter is Dimitri from Subsurface Dynamics. I'll throw his bio up in the chat. But of course, that's what Kevin was showing integration with. So it's a wonderful segue into Dimitri's presentation.
Hello,
Darcy,
everybody.
please hit the video.
First of all, thank you so much, SAGA, for inviting us for such a great event. Let's try to make it a weekly event. My name is Dmitry Derushkin. I'm with the Subsurface Dynamics, and today I'd like to spend a few minutes talking about the subsurface automation and Athena automated workflows. So just as an intro, let's just define what Athena is and what we do. So Athena is not a product. It's a process of automation and integration. So our goal is not to reinvent the wheel over and over again. Our goal is to automate engineering workflows. So we believe in 4 simple principles. 20-80 principle. So we believe that engineers can achieve 80% of results using 20% of time and resources, especially in today's environment when everybody's super busy and wearing 10 different hats. You do not need to be a power user to perform a daily engineering work. We believe that all tools are clunky and overcomplicated, and the further we go into the woods, the more complex and clunkier they become. And we believe that simplicity, automation, and integration are the key to the industry future. So just to look at Athena at a glance, one of our goals is to fully integrate all available sources of information. In our case, we're collaborating with Petra Ninja, so we're grabbing all the data from them. If there is a SCADA connected through the system, we getting access to that data. And then on top of that, we have proprietary Subsurface Dynamics database that we all feed together into the Athena workflows. And then as a brains, we have 3 different tiers of workflow. So the first will be simple analytical methods. It's all well-known methods that have been invented and reinvented several times over the last 50 years. And we have physics-based methods, which are more advanced ones that you typically used in a detailed engineering studies or integrated engineering studies. And we have tier 3, which will be machine learning type of tools. So by combining all those together, what we can do is we can pretty much automate our deliverables for the purpose of production forecasting, economics, field surveillance, and production optimization. I'm not going to talk about features and capabilities, just quickly show the workflow. So it's pretty much you can grab any well list from the Petra Ninja and directly throw it into Athena. You can process all the wells. By default, it will grab the government data set, but if it's SCADA connected, it will grab the high resolution data. That pretty much can be daily, hourly, minute, as dense as it's being recorded. From here, you can take on any type of workflows you want. So you can pretty much go through your wells, QC them, look at the forecasts, play with the scaler, see how it will look better, if there is any problems with the wells. Then if you see any bad forecasts, like this example over here, you can go to the production forecasts, and you can adjust those properties either manually, or you can still use the auto-fitting algorithm, and you can just lock certain properties. It could be decline rates, it could be starting month, ending month, and so on. And you can automatically apply to all your wells. So as a basic outputs, you get all your EORs, you get all your production forecasts. You can export them, you can switch to different views, you can switch to different fluids, you can look at your GORs, water-oil ratios, and so on. So in general, it has all basic capability that's required to perform the daily tasks. After you're happy with your forecasts, you then can go to the generating type wells, or you can go to generating group wells. So all this done on the fly, on the cloud, so you don't need to do anything. There is no requirement for additional hardware, software, or anything like this. So it's pretty much all web-based. Then this is the example of the group well with the GOR overlaid on it. So you can switch from the rate cum to the rate time, check different fluids, make sure that you're happy with it. And then if everything seems to be in order, then you can perform, then you can go to the economic forecasts. And over here, it gives you the opportunity to change your economics parameters, play with your cutoffs, play with your price decks, play with your commodity prices, royalties, OPEX, CAPEX, and so on. So for the clients that have SCADA integration, we can actually grab this data directly from their internal databases, so they don't even need to worry about anything. So each and every well within different vintages will have their different values for the economic analysis, and they can be automatically integrated into the workflow. So on top of that, if we want to, the economic analysis itself, it can be done on the type well, group well, single well. It can be done for the whole production period plus forecast. On top of that, if you want to do any type of forward looking modeling, so you can easily switch to this mode, and you can play with your parameters and see how it works, and if it actually makes sense to go do workovers or do any other additional things. So going back to the case study, so I showed the basic capability, and it's kind of it's available, like the demo version is available for free. You can just go and log in through the Petra Ninja website or through the Subsurface website. But let's talk about the workflows itself and what is the motivation behind all this workflow. So as Kevin was previously showing, we were looking at some Montney, different Montney vintages and different Montney groups of wells. So what it allows us to do is pretty much as an engineers or the business development guys or the acquisition A&D guys, it allows us to evaluate our assets or neighboring assets very, very quickly and very, very efficiently. So this particular example showing the some Montney wells that we analyzed. So on the left one, it will be older vintages, and on the right one, it will be newer vintages. So say we're going for the to place the well and to select the completion design that we want to pump on our asset. So like the general workflow would be, you would be going, like you either go into the detailed studies, which people not very often do due to budget constraints, or you can just go into any available databases and you can start searching through the wells, previous completions, try to understand what was done and how you can apply to your asset, right? Which takes astronomical amount of time. Like nobody has time for this. So, and the idea behind it is you can simplify your workflow, especially if you're working on those assets, you know, indicators that you want to look for, and you can narrow down your search, and you can narrow down your potential completions and potential key drivers within the reservoir very, very quickly. And that's what this tool is designed for. So for instance, if you look over here, without going into the details, and please power users, don't throw rocks at me, but this is the very simplified workflow. So what you can see over here, it's pretty much, if you look at our GORs, you can if you look at our declines, you can see that the older vintage wells, they are producing not as much, but their decline is much more stable. And if you look at the newer ones, you can see that the initial productions are pretty high, but then the declines are quite dramatic and significant. So it depends on what we're trying to achieve. We can go both routes. But let's say we want to develop a pad and we don't want to be as aggressive on our completions as the new vintages. So we can easily take those wells, take this two group of wells, and we can easily look at indicators that will show us overstimulation or parent-child interaction or any problems that we can experience over there. So over here, if you look at these wells, exactly same group of wells, you can see that, for instance, on the left group, on the older vintages, the GOR doesn't spike as much. And if you look on the right one, you can see the GOR goes through the roof pretty quickly. As a result, you have higher declines and you have a detrimental effect on your production. So from this, you can conclude that, well, maybe for the new vintages of well, we can either have, especially for those who work Montany a lot, they'll know that, well, that could be parent-child interference, that can be overstimulation, or we just placing our wells too close, right? So, and then another thing we would want to look is, again, for the guys with the multi-bench development within the Montany, we want to see how our water behaves, right? So, and if you look in the older vintages, the water oil ratio is much lower, and if you look at the newer one, it's quite high, significant, and it actually spikes at the end pretty dramatically. So what it will tell us, so potentially some of the wells within this group, they're not landed very well, right? So we need to be cautious about that. So, and on top of that, if you have a SCADA system connected through Athena and Petra Ninja, what we will do, and part of our standard workflow, is we will do the production surveillance. So it's pretty much Athena will watch and notify you if anything unusual happens with the well on production. So you don't need to spend your time doing it. You don't need to evaluate it. And now you can actually predict those things rather than react to those things. So, and the things we're typically looking for, they're very simple, but at the same time, they're quite complex. So we're looking at the liquid loading, pump breakouts, or any artificial lift problems. We're looking at the freeze-ups that happen a couple of months, non-optimal drawdown strategies, and any abnormal production behaviors that we don't want to see on our assets detrimentally affecting our production or economics at the same time. So, and for the visualization purposes, what we can do is we can push. So we perform this analysis. We define two groups. So now we know that, for instance, these wells, they're better producers. They have a more optimal drawdown managements. They have better placement. And if we compare it with a second type of group that have elevated GORs, higher water, and all other issues like the very aggressive declines, if we want to optimize our completions by looking at the nearby wells, we would probably want to focus on this group of wells, right, rather than this group of wells, because we want to have the producers like those. And for the visualization capabilities, now when we have those groups, and you can go like into as many details as you want, you can overlay the geology, you can overlay the different benches, landing depth, and things like that. So you can break it down into as much technical details and granularity as you like, but the ultimate goal and the ultimate benefit of doing it this way is it takes you 10 minutes instead of 10 days prior to that, where you had to dig through all this data and you had to like either import it into some third-party software, or you had to like use any commercially available tools that are not integrated, just to understand those simple things and simple indicators, you would spend much more time than you can do it today. I guess on that, thank you so much for giving this opportunity to present.
All right, wonderful presentation, Dimitri. Thank you for answering some of the questions that have already been coming in on the chat. So we are now through halfway through our lineup. So we're at the halftime show. We're moving on to one of my best buddies here, James McDonald, who I used to work with at FICAD and IHS. He has moved on to join Inside Petroleum, where he's been, I'm not sure now, Jimmy, probably the last half year. And he's representing Combo Curve, which is one of their main products in the market. And James will talk about the benefits of what Combo Curve can do. And with that, Darcy.
Hi, everyone.
Cue up the real
my name is James
JMac.
McDonald.
Thank you.
First and foremost, I'd like to thank SAGA and the team for inviting me to be part of this video series. SAGA, I love everything about what you guys do for our industry. Keep building, keep growing. So the use case for the talk today is to have a discussion regarding the implications of the decisions that we make when building type curves, right? Specifically as it relates to the parameters we choose to normalize by and the normalization types. Keeping with the theme of introducing new technologies, the new asset management tool doing the work for today's discussion, or it's done the work for today's discussion, is Combo Curve, which is an Inside Petroleum product. So a lot of things that I can't show with slides is the speed and efficiency of being able to forecast or mass forecast wells, build type curves, apply those to existing or future well locations, schedule when they come online, and then run detailed economic scenarios, all in minutes, all in one place. That being said, a part of this asset management tool, one of the things that you can do is type curve creation, and which is the major focus of the talk here today. So you're seeing kind of the four big questions that I really want to attack here in this talk. I mean, when it comes to analyzing production data as a whole, we certainly should and do scrutinize and question everything about analyzing that data. So then certainly worth mentioning that, take advantage of all the information that you have. You'll see that kind of come up here in a couple of minutes. And then keep your ears and eyes open for new methods and new ideas about analyzing production data. So to discuss the case details, so the wells that I selected for the work that we did here, we're going to look at here today, is wells that are in the southern Delaware. These are all oil wells landed in the Wolfcamp Bay that have at least 24 months of production. So what I had done was identified this well set and actually went in and took out some wells that were in the middle. There's actually 42 wells that I removed here from the middle. So I did all my type curve work with the wells that you see here on the outside. And then we're going to walk through the steps of the work that I had done, and then went and applied then that understanding of those type curves to these wells in the middle, and then evaluate that, and then we'll look at those results together. So step one, when it comes to wanting to build a type curve, it's a good idea to have your production history, which is obviously important to have that recorded history, but then actually couple that with your best estimate of what the behavior of those individual wells looks like into the future. So really what I'm saying is go ahead and forecast all of your wells, which is obviously easier said than done, because when it comes to forecasting, there can certainly be a lot that comes into it. And the impact of how you choose to forecast your wells is certainly going to be an important key when building your type curves. So what I mean by that, and just to kind of pick on a few of these categories, is the forecast type. Do you want to do a rate time forecast, rate cum forecast? Do you want to forecast on your ratios and then use those to calculate your secondary phases? When it comes to creating your type curves, just looking at one phase, you still need to create your type curves for all your phases. Everything that comes out of the well is important. So then the actual model that you want to choose, right? There's certainly a large number of models out there and available. So then which model do you want to use to go ahead and fit your production data to create your forecast? Selecting the duration of how much time do you want, if not everything, if not all of your data, well, how much of your data do you want your decline curve to fit to? And then inside that data range, maybe you have to make a decision of what you want it to look for, because there could be a lot of things happening inside that data range that you'd want to identify. And even little niceties like being able to put additional emphasis on which parts of the data inside that range, after you've identified it, do you want to put additional emphasis on? Right. So a lot of things that go into forecasting your wells. But once you've got your forecast built, always nice to look at your well set a number of different ways. So you've got a rate time, a cum time. Here's your EUR well collection. Being able to cross plot by a number of different options, or maybe even take a peek at the map. All of these, different ways of looking at your data to see if you identify wells that maybe you don't want to include as part of your type well. Maybe for some reason something sticks out that's not as analogous to the type well to the rest of these wells, so you just remove it right from here. But if you're happy with your well set, this is actually a really clean well set here. Before I took the screenshot, that if you're happy with this well set, then we can move on to really kind of the bigger topics and bigger conversations that we want to have. So first and foremost, normalizing parameters. So there's, the parameters that we can account for to and try to determine its effect on your production, the production of your wells is essentially limitless, right? And I don't mean limitless of what parameters you can use in the software to try to normalize by understanding. I'm saying there's a number of factors that contribute to the behavior of your wells, and some are certainly more important than others. And really, my biggest goal here is to try to identify which parameters or combination of parameters are having the biggest effect on my wells, which would then lean towards these are the ones that I certainly would need to focus on for this area when normalizing my production data. And part of that to say that maybe, I'll say lateral length is a given. If you're talking about unconventionals, okay, lateral length, I'm going to grab you, I'm going to put you here, I'm going to use you no matter what I do. But in addition to that, maybe, well spacing and cluster spacing or stage spacing are very important parameters in one area, but then you find, net pay and proppant intensity have a much bigger effect in another area. So it's a lot of this to say that the exercise of trying to identify which parameters are the most important is something that you should do every time you're building type curves, no matter where you are. So then, for example, here in my case, what I had done was I ran through an exercise and I went back and forth a number of times, grabbing parameters and combinations of parameters, quickly, based on the parameters that I grabbed, quickly create a type curve, fit it to all of my wells, and then quickly get this. There's a number of metrics, error metrics that we'll calculate. And this, I'll just pick the really simple one, just showing your cum diff of determining how that type curve that I quickly built with whatever parameter that I built, how good of a job it's doing fitting my wells. Really what I'm looking for is the one that has the least, and keep an eye on the scale here. It's going from 1 to -1 to 1.5, and here's going from -5 to 0.5. The one that has the lowest amount of error seems to be doing the best job of fitting the majority of my wells. So you could certainly come up, you don't have to just pick one set here and then move forward and go on to the next step. You could move forward with different possibilities of combinations, but just for the sake of simplicity, the story that I'm telling, I just went with one set of combinations of parameters that I thought was having the biggest effect on creating or affecting my wells. So that in my case, that actually ended up being the completion fluid. Right. So what you're looking at here is a quick chart that's showing the your EUR per foot, barrels per foot of your EUR, and then the completion fluid, barrels per foot here. And then that was me identifying that parameter, and then I move on to the next phase. I will say that most of the work that I'm showing you, these were all oil wells, so most of the work is identifying oil wells. But important to note that I did all of this work on every one of the phases for all of the wells. I just didn't, trying to limit the number of screenshots. I'm not showing every individual phase, just focusing on the main phase for these wells, which was oil. So then now that we've got our parameters that we want to, the most important driving force of a parameter identified, so then the next step could be now I have to choose a normalization type. All right, so which one of these do I want? So then the options are one, I actually went and created cases with no normalizing at all, just use the raw data and then go create some type curves and then move forward to see the effect that would have. But then some of the other options that we have is a quick one-to-one fit, which is really just very simple. So say, for example, I'll grab this dot here right at the top, which is approximately 80 barrels of EUR per foot with 40 barrels of completion fluid, or barrels per foot of completion fluid. So then just to say that if I doubled that intensity to 80, then I would essentially double my expected output in this case. So a quick one-to-one fit, very simple, easy to use. It actually still gets used an awful lot, but like I prefer, and a big part of this talk, and you'll see when we start looking at the results, is to maybe start looking at other methods that might do a better job of providing a better understanding of what the expectation of future well locations might hold. So then a very simple one, but again, very, very powerful, is a linear fit. So then the idea here is that the slope of this line, right? The slope of this line is really contributing that input to output relationship. So that relative change is controlled really by the slope of this line, but it is a straight line, hence linear. That being said, so then moving over to what I'm calling power law here is actually an example of a nonlinear fit. You can see there is some curvature to this line. And really what it does is do a good job of accounting for diminishing returns as we get further out. And that's kind of a big point of kind of going from here to here to here, is the assumption that you know exactly what, if you just put twice as much of something or cut something in half, that's going to affect your production by that exact same amount. In some cases that it's close, right? And it works out fine, but in other places that doesn't necessarily bode very well. So then going through these exercises of using multiple methods becomes very convenient. So then that's the answer to the question. You're saying, well, which one of these methods did you choose? I said, well, that's why we're here. I chose all of them. And then I create type curves with all of these, and then we'll actually do that comparison here together. So then the next step would be to go and actually do our fit, right? So we still have to fit our data. So you can see the well production here in the back, and then I've got my type curves sitting on here. So, I mean, overall, this looks nice. It looks pretty. No reason to believe that this isn't necessarily a good set of distribution of type curves that I could go apply to my wells and do my work. But really the question is what am I actually showing here? Like, what is the answer as to how these type curves were created? And one way to kind of question that is showing it on here. So what I'm showing you is the same type curves. Like, this is the exact same answer for the left-hand plot on both of these. The chart on the right-hand side is showing you the well collection EUR. So this is the individual EUR of all of the wells that are in here. And then the dotted lines is just going through what would be the P10, P50, and P90 points of that well collection. So then the solid lines represent the EURs of those, the answers that came from here. So the way that these EURs, the way that these type curves were drawn, that gives the EUR values, is just a simple time slice, right? So at every time period, go calculate a P90, 50, P10. Next time period, P90, 50, P10. You get all those dots and you try to draw a line to stitch it through every one of those points as well as possible, best fit those points, and there you go. Well, by doing that here in a case like this, you'll often end up with an answer that looks similar to this. Your P10 isn't actually going through the P10 point of your well collection. It's sitting really close here to the top. And what I'm saying is that if you went and selected these wells, and then you went and chose how you were going to forecast these wells, it should be reasonable to assume that the P10 of your wells, from building your type curve and all the work that I've done to get to this point, should come to being close. It doesn't have to be perfect, but ideally fit within a minimal error percentage of the actual P10 of your well collection. I actually should have put some references. This isn't an original idea. There's a lot of documentation on this as well. And I could put a reference in here. I should have put a reference in here before we had this talk. But then one of the things that you can do is, like, for example, one of the buttons, like, there's a number of ways to fit type curves to data, right? Like, this isn't just, this is one of many. So then this one button that you can apply in the software will force your type curves to fit the P10, P50, and then P90 points of your well collection, which is great. But I actually like using this as a guide, right? If I'm making choices and decisions of how I want to fit, because there's a number of other ways that you can fit these options in the software as well. If I'm coming in here and I'm selecting different methods, I like applying a different method and then seeing what the results look like on my well collection. Or even if I actually go to the manual mode and I stitch together. I use multiple individual segments to stitch together my own type curve. I like finishing that work and then coming in here and then seeing what that result looks like on something like this. So at the very least, use it as a guide, but if you wanted to, you could actually just hit the button that comes in here and it automatically fits this for you. So in this case, I identified my parameter, I selected my all of my normalization types, and I came and actually did my fit. And again, did that work for all of my phases, but I'm just showing the one phase here. And then, so here's us taking a look at what those results look like. So here's actual type curves that came from all that work. So then the bright lines represent the linear nonlinear fit. So then the solid bright line is our linear fit. The bright dotted line is the nonlinear fit. And then the dimmer lines, or the more shaded lines, the solid one is the one-to-one fit. And then the dotted line is our normalizing. You'll see that the shaded dotted line is out to lunch on all of these as we go through them. The ones to kind of really keep an eye on the most would certainly be the linear and nonlinear fits. So I'll just go through these. So these are actually wells that were part of my selection. The wells that I used to actually create the type group. So it makes you think, well, obviously you'll fit those pretty well. And not necessarily, right? Because there's always going to be some outliers. But I just kind of went and then did a quick back check on the actual wells that I used to create the type curves to see what it kind of looked like. So then after that, the goal was to then apply all these type curves to all of the wells that I had omitted from my well set at the beginning. And then that's what we've got here. So then looking at the fit, and I could talk for every one of these individually, you could probably get into the weeds a little bit. For the most part, you tend to see kind of a consistent, the ones where we actually applied a normalization factor is doing a better job of fitting the data than the one where we didn't do anything at all, right? So take that guy out. So then it becomes, well, which one of these is kind of our preferred method? You could certainly walk through the options of walk through the options. You could certainly go and look at your wells. Well, if you've got 500 or 1,000 wells, which would be a ridiculous number of wells for creating a type curve, because it'd be hard to see anything. But I mean, still, let's see, even if we have 300, 400, 500 wells, that's a lot of wells for you to start looking at every individual well to see, well, and then start checking off. It's like, I think this one is better here and that one's better there. You could certainly walk through looking at wells, but then using some calculations to try to help you determine those error metrics is certainly more of a benefit. And before we look at one of those or some of those, I will say, I forgot I put a slide in here to say that these aren't all heroes, right? There's certainly cases in here where there's wells that just don't fit the style or that don't jive at all with any of the type curves in the least. So our goal overall is to come up with the option of a type curve that does the best job overall of fitting the majority of the wells, right? So then a way to quickly look at that, and again, this could be an example of kind of going back and forth, is looking at, again, so we were looking at cum diff when I was talking about error metrics before. Here's a look at looking at relative error and then absolute relative error. The combination here at the top, so this is the same parameters for one of the cases. This is where I used, I wanted to show the worst one. So I used the one where I had no normalizing at all. This is what it turned. Here's what the error metrics kind of look like. In this case, this is actually using the linear option the nonlinear option, so the power law option of fitting our data, and then really just looking at the difference between these two charts, seeing how we can limit that error in our fit, and again, as in kind of an overall number. So it's leading me more towards the linear, but you'll see the linear to not the nonlinear and linear both do a decent job in this case. But it's nice to be able to quickly run through all of these options and then look at the numbers and look at the metrics and try to make more sense and not just blindly trust that we're building type curves on data and, well, here's my average and here's a curve and I'm just going to go ahead and put this on here and hopefully my asset valuation is reasonable and move forward after that. So then that leads to then actually applying some economic evaluations on here. So I didn't put too many charts in here to really kind of show this off because I'm trying to keep this under, I promised John I'd keep this under 20 minutes and I think we're getting close to that. So what I'm showing here is a discounted cash flow. Discounted cash flow through time, right? So we're actually calculating the monthly cash flow for every one of those cases. So this is the 42 wells. So the asset has those 42 wells and then showing the total economic cash flow, discounted cash flow, 10% discounted cash flow for every one of these. But where it actually kind of shows off a lot better is looking at the cumulative values of these through time. And then what I did was just show what the total cumulative. So this isn't even the entire time. This is just the first 6 years of production, which still accounts for the majority of our production, you can see that we're starting to get into pretty low depletion here on most of these. So it certainly accounts for the majority of what our cumulative cash flow would be. But you can certainly see like a $65 to $70 million difference of total delta if I go from no normalizing at all to my biggest number here, where it came from my linear case. So it's just to say that's still a big difference. So maybe another way to look at this that tends to make a little bit more sense, or a way that is very popular to look at your asset or your scenario, is to look at your waterfall charts. So again, just listed here by which method we're looking at. So you can see all your revenues and then all of your expenses, and then what that total discounted cash flow is for every one of these. First, in this case, first discounted cash flow for us just means a 10% discount. Just so we know what we're talking about here. So the total delta in this case, for looking at not just its first 6 years, but the entire asset for the entire lifetime, difference here in this case is about 80 million. So certainly, yeah, or maybe even closer to 90 million. No, 80 million. I thought that is Nate. So all of this to say that, to kind of reiterate everything that we put into here and trying to make sense of this in a very short period of time, very important for you to want to go ahead and get an understanding of the parameters that you have available to you, and then using a number of those to identify which ones seem to have the biggest driving factor behind the production of the well. Normalizing, and I find I do this a lot, right? I'm not sure which normalizing tool, like norm, linear, non-linear, I don't know which one I'm actually going to use going in. I'm not going to go in blind. So I tend to find myself using a number of these and then kind of running through to the end to see what the results end up looking like. So then the error metrics become very useful for being able to quickly look at, hundreds of wells and applying type curves to hundreds of wells, and then seeing which ones seems to be doing better, just comparing which case seems to doing a better job of fitting the majority of your wells. And then you want to quickly see the difference. Like if I choose to go linear or non-linear, what is the economic impact of that? And then be able to quickly kind of string all this together. I'll say like all of this work took me very, very little amount of time. It didn't take a whole lot of time to do. It actually took me more time to figure out what asset or which well set I wanted to use than really kind of go through and create all the work. But thank you very much for your time today.
All right, James, great presentation. Thanks for that. I've got to know, what's the answer to the poll question regarding the NHL goalies, who's got the most points in a game?
Oh, I just named Mike. Well, assuming that there was going to be a number of people from Calgary on the call, I wanted to make it a little bit specific to that. So that kind of gives away the answer. Jeff Reese, February 10th, 1993, got 3 assists in a hockey game. That's great. That's what I wanted to hear on a Friday, Jimmy. And this was a great presentation. Thanks, James. Continue to ask him questions in the chat. He's going to be around to do that. We're tight for time, so we're transitioning to the infamous Scott LaPierre. For those of you who don't know this name, you're under a rock. He's been trying to spend the last few years rattling cages and telling people about the impact of GOR and how that influences oil rate decline. He's come up with a new method that he wants to show you about his early predictions of hitting boundary-dominated flow with GOR diagnostics and how to forecast wells more reliably, with an emphasis on the Permian. So with that, we'll transition to Scott LaPierre from Shale Specialists.
John Thompson, Dave Anderson, thank you so much for inviting me to participate today. My name is Scott LaPierre, and I'm with Shale Specialists. We are a small consulting firm with headquarters in Houston and the Denver area, where we focus primarily on research and developing solutions to high-value challenges faced by the oil industry today. We also provide a very unique brand of comprehensive, integrated geological and geochemical, petrophysical, and reservoir engineering modeling services to help investors, reserve-based lenders, and operators make more accurate forecasts and determine optimal well spacing. I have this disclaimer. You can pause this and read it. The title of my talk, New Life for Old Math, is a reference to this 2014 article, which drew attention to the fact that the primary, one of the main tools we use to forecast oil reserves in the shale industry is, in fact, ARP's decline curve analysis, which is quite old. Now, rising GOR did catch the industry off guard. And if you don't believe me, just take a look at these these presentation materials from investor conferences where you can see early percent oil being propagated far into the future, which is basically demonstrating that at the end of 2018, this operator had no expectation of GOR rising. They're not the only operator. Here is another operator clearly projecting initial GORs as flat forever into the future. Here's yet another operator doing the same thing. Unfortunately, when GOR started to rise, some CEOs still misunderstood the implication of the rising GOR.
And then finally, there's been some concern about your gas cuts. Can you just talk about whether there's anything to worry about? Thanks.
No, I think based on, I was heavily involved in the analysis, being an ex-reservoir engineer and what happened. I've come back and looked at a lot of the data, and so there are essentially no issues. Over time, the gas-oil ratio is going to increase. It will continue, and it's a plus. So it has not affected the oil cut at all.
Now, unfortunately, comments like that are in stark contrast to sound reservoir engineering principles, such as those displayed by Steve Jones from Cimarex in his 2016 publication, where he was able to history match the observed transitions in both boundary-dominated flow and escalations in GOR upon encroachment of the bubble point. He's not the only one to have done so. Here is a 2017 publication from Koshkagem et al., which includes Professor Lee, clearly showing that a transition to boundary-dominated flow is preceded by and associated with severe escalations in GOR prior to the degradation in oil declines associated with boundary-dominated flow. So it's unfortunate when a CEO makes those statements, because you can imagine the technical staffers being placed under great pressure. I can only imagine what kind of pressure that might be. Now, DCA is widely used, but it's also heavily criticized. Some of the advantages of DCA center around the fact that it has very minimal data requirements and it's easy to use. Also, there's really no practical alternative for people who need to consider oil reserve estimations on thousands of wells in a short period of time. Some of the disadvantages are that it was originally intended for boundary-dominated flow in conventional reservoirs. So with the advent of multi-year transient flow periods of shale wells, it is really out of place in its application. Also, purely empirical. It was not based on any original reservoir theory. However, later it was justified to be consistent with theory by other contributors such as Fetchevich and our own Dave Anderson. Now, there are challenges with traditional application of decline curve analysis in shales, and they center around this multi-year initial infinite acting transitional flow period that is typically characterized by a very large B exponent. And of course, a large B exponent severely flattens declines over time, meaning if you don't do something to modify your forecast, you're going to end up with an infinite oil recovery. Of course, late life introduction of D-min, or a constant rate exponential decline of 5 to 10%, basically implies that the boundary-dominated flow transition is going to occur decades into the future. Also, some of the challenges are that DCA lacks any internal mechanism for predicting the transition to boundary-dominated flow, which would be handy given that these boundary-dominated flow transitions are occurring sooner and sooner. There are other alternatives, such as rate transient analysis and RTA, but they're not immune to this BDF prediction challenge. John Lee has taught us in some seminars to try to overcome these challenges by the use of analogs and reservoir simulation and field experience and type curves. But he points out that it's very important to control these forecasts. Now, it would be fantastic if we could see past the infinite acting period towards the finite boundary dominated period while only having data from the infinite period. And as you can tell, perhaps from the title of my talk, I believe I found such a way, and I'm going to present it to you today. And this is specifically important because as we have tighter and tighter spaced wells, larger and larger fracs, we are seeing earlier and earlier transitions to boundary-dominated flow. Now I'm going to use GOR as part of that signal, and I just would like to hide behind the leadership of Steve Jones from Cimarex for his use of GOR data from transient flow periods to glean information about the boundary dominated flow period, which in this case he was using it to determine oil in place of the drained reservoir volume. So the idea that there exists a signal in transient flow that can say something about boundary dominated flow is not new to me. So let me just organize how I'm going to achieve this. I'm going to compare early time traditional DCA applications with those performed on the full production histories from some aged wells. And these wells will have already transitioned to boundary dominated flow. Oops. Then I'm going to introduce a novel reservoir signal incorporating the GOR. And I'm going to establish the context for my proposed predictive capability within established physics. And then I'm going to demonstrate how to cultivate and leverage this precursor signal to modify early time forecasts. And then we'll compare the results. Field case number 1 is a DJ Niobrara that is fully bounded on both sides with an average spacing of 420 feet, and it was placed on production in 2013. The graph on the left is my rate time plot, where the white represents oil per day and the green represents oil equivalent per day. And I should note that all of my oil equivalencies will be on a 2-stream basis with a 61 energy equivalence. Now I have fit an early time forecast through this data as represented by the white dash, and it is an objective regression. It is not artistic subjective. And in here you can see the same data and the same forecast on a rate Cume plot. And I've also included the GOR data and that classic flat forever assumption used by so many oil companies. And then I also added the implied transition to boundary dominated flow from a 7% dmin assumption, which is like on day 3000 and upon the production of the 144,000th barrel. Now, unfortunately, when we look at all of the production history, we see that this oil decline has, in fact, deviated from our initial expectation in connection with steadily escalating GOR. And in fact, when we look at an RTA plot, we can see a rather classic -1/2 slope transitioning into a -1 slope right about here. So this is evidence suggesting we've transitioned to boundary dominated flow. However, when we perform a full history 2-segment decline curve analysis with objective regression, we observe that yes, in fact, boundary dominated flow did occur on day 772, and it manifests as a 27% constant rate exponential decline. And that this new forecast shows us, in fact, that we can expect about a 50% shortfall in oil production over our traditional late life BDF assumption forecast. Case number 2, this is actually 15 wells together as a composite average. This is 15 wells from an infamous cube in south central Midland County. These wells are fully bounded on each side. They have an average spacing of 315 feet, 3-dimensionally, and they were placed on production in 2016. As you can see, here's my early hyperbolic decline forecast through the oil data, and here is the 7% dmin assumption indicating that boundary dominated flow will occur on day 4000. Now I have taken my GOR assumption of flat forever, combined it with this oil forecast to produce this flat total energy equivalence production. That's why it's parallel, because it assumes GOR flat forever. Unfortunately, when we see the full production history of these wells, these are 15 altogether, we see that oil production has, in fact, fallen short of our expectation in connection with steady escalation in GOR. And when we look at a rate transient analysis plot, we see a group of wells that collectively march along the classic -1/2 slope, and they all transition right here to a slope of -1, suggesting that this in fact is boundary dominated flow. And if we perform a second segment, full history objective regression of decline curve analysis, we find out that yes, boundary dominated flow occurred on day 441, and it was manifest as not a dmin and a B exponent of 0, but in this case, it was manifest as a B exponent of 0.62. And unfortunately, we see that we are going to experience a 50% shortfall in oil production relative to our traditional late life BDF forecast. And finally, case number 3, this one doesn't have as mature of a production history, but because it's so new and it's from such a prominent operator, I thought I would include it. These are fully bounded wells in Midland Basin with an average spacing of 425 feet, all placed on production in April of 2019. When we look at the rate transient analysis plot, we see that we have a march of data along the -1/2 slope, transitioning to a perfect, albeit short, -1 slope. And this is only the last 5 months of data. But this data only goes through January of 2021, so perhaps this operator can provide us an update with more recent data to see if this boundary-dominated flow has in fact set in. And that, of course, manifests as a 60% constant rate exponential decline on day 388. And unfortunately, it seems that we can expect a 62% shortfall in oil production relative to the traditional late life BDF assumption. Now that I've established some cases to work with that have in fact transitioned, now I want to introduce the novel reservoir signal and then place it within the context of established physics. So let me start off by asking this question. After we're on production, after we're on reservoir response, or we're on gas lift, or the ESP is set steady, we've cleaned up, can the total fluid production from a well ever increase? Well, yes, it can. We see that all the time if we re-energize the system with an offset frac. And we could also see it if perhaps an operator has spare capacity on their ESP and they turn up the knob, then they're re-energizing the system that way. But in general, we are used to oil wells and gas wells declining over time, and we would never expect production to increase. All right, let me ask it a different way. Could we ever sustain a total energy production in barrels of oil equivalent sustained indefinitely with increasing time? In other words, if we're on reservoir response in our hyperbolic transitional flow decline period, and we're not adding energy to the system, what would happen to the GOR or to the oil production that would result in us actually experiencing an increase into the future of total energy production from a well? Well, there's really only one way I can think of that, and that would be if the energy density of the produced fluids would increase. In other words, if the well would get oilier and not gassier, then perhaps this could be accomplished. We would need the production stream to be dominated by heavier hydrocarbons with more energy density rather than lighter hydrocarbons with less energy density. And of course, that's not what we see. We see rising GOR. We see decreasing oiliness. We see decreasing energy density with time. And by the way, I just want to clarify again that I'm using BOE per day as a unit of energy. BOE is a unit of energy, just like joules and BTU and calories. And as long as we agree on an energy conversion ratio, it's a unit of energy. Just wanted to clarify that. Now, when we think of it in terms of energy, is there any physical laws that might restrict an indefinite rise of total energy production from a well in the state where total fluid production is decreasing continuously into the future? Well, the restriction that comes to mind for me is the law of conservation of energy, which states that a system always has the same amount of energy unless it is added from the outside. So if you consider the entire wellbore, reservoir, surface tanks, everything together as just one system, and it's a closed system, then absent the addition of energy, we can expect the total energy of that system to be the same on day 1000 as it was on day 1. And if we were to ever see in our hyperbolic early time transitional flow forecasts any combined trend that would indicate a future sustained increase in energy, then we would be violating the law of conservation of energy, which I like to call the energy wall. And I encourage you to go try to simulate this in the reservoir. I want you to try to simulate rising total energy production with rising GOR and declining total fluids production. I don't think you'll be able to do it. Now, energy wall, the law of conservation of energy, is really a macroscopic sort of picture. It doesn't connect us with what actually has to happen, but it just says something has to happen. But I think if you go through the various iterations, there's plenty of reservoir engineering mechanisms that you can model that will produce this result, such as the post-bubble point relative permeability at critical gas saturation issues, or the achievement of boundary-dominated flow. Or you could model it, as my personal favorite, exhaustion of primary drive energy at the bubble point. Either way, these will provide what is absolutely required by the universe, and that is the GOR trend has to lessen and or the oil decline has to worsen. So now let me demonstrate how to cultivate and leverage this precursor signal of breaching the energy wall to modify an early time forecast, and then we'll compare the results. Here, back to field case number 1, where we observed a boundary-dominated flow transition manifesting as a 27% constant rate exponential decline on day 772. If we return to our early time hyperbolic segment, and then we look at the full future history of GOR, and then just combine this hyperbolic segment with this trend in GOR to generate a gas forecast. And then if we combine that gas forecast to the oil forecast in a simple two-stream 6-to-1 conversion, we produce a total energy production forecast, a total energy production per day forecast. And we can clearly see that this hyperbolic segment with this GOR behavior would result in a breach of the energy wall. And if we go back into our decline curve analysis and say, how can we change our objective 2-segment decline curve analysis in a way that will honor this oil production behavior and this full GOR behavior? The only thing we could possibly do to make that happen is to invoke boundary-dominated flow via a 24% constant rate exponential decline on day 855. And this compares quite well to our 27% that we observed on 772. Now that's not super close, but the good news is that these two models' error is within 3% of each other. So this would suggest that if we can reliably forecast GOR into the future, we might have a way to sanity check our initial hyperbolic decline forecasts against breach of the energy wall to predict a transition to boundary-dominated flow and greatly improve the accuracy and reliability of our early time forecasts. If you remember case number 2, where we encountered a boundary-dominated flow on day 441, if we return to the hyperbolic segment and then look at the full history of the GOR trend and combine it with this forecast of the hyperbolic segment to generate a gas forecast and then to generate a total energy equivalent production per day forecast, we see clearly that this system was headed for a breach of the energy wall. And the only thing that we could have done to prohibit that breach, but still honor the GOR behavior that was going to come afterwards with this early time hyperbolic oil behavior, is to invoke boundary-dominated flow via 0.62 B exponent on our second segment. And so that, again, is an example. If we can reliably forecast a GOR trend into the future, then we should be able to dramatically improve the reliability of our early time forecasts. And then field case number 3, this was the prominent Midland Basin operator, recent cube, 10,000 footers, all popped together. Again, if we return to our early hyperbolic oil decline and then combine that hyperbolic decline with the observed behavior in GOR over the entire life of the well, we see that the total energy equivalent production per day is in fact headed toward a breach of the energy wall. And the only thing that we can do from a DCA perspective is to invoke boundary-dominated flow on day 421 with a minimum decline of 56%. And that compares really well to our actual boundary dominated flow of 60% on day 388. And again, the two models are within 5% of each other in terms of error. So again, it looks like that if we can forecast GOR into the future reliably, then we would have a new tool to modify our early time forecasts to improve the reliability of early time forecasts. So now let me conclude and review. I hope I've demonstrated that GOR escalation at boundary dominated flow and at bubble point is perfectly consistent with known reservoir theory. And I hope I demonstrated that that I'm not the only one to propose that a signal from GOR during transient flow periods may be able to tell us something about the boundary dominated flow period. That honor goes to Steve Jones. And I hope I demonstrated with my cases that I selected that the observed boundary dominated flow transitions that have objectively manifest already are exceptionally coincident with breach of what I've introduced to you as the energy wall. So the next big question on everyone's mind ought to be, well, how reliably can you forecast GOR into the future? And unfortunately, we run out of time. I'm not going to be able to talk about that. But I will share briefly some observations from my 5 years of continuous practice of this technique. First of all, the transient signal strength, this clear impending breach of the energy wall, is highly correlated to well spacing, higher percentage drawdowns, and continuous GOR behavior. Also, the bigger the B, the better. When you have strong hyperbolic initial declines with any sort of escalation in GOR, the future indication of a breach of the energy wall is quite obvious. Now, the good news is that a lack of a signal of a clear breach of the energy wall simply results in no modification to the forecast. In other words, you're simply left to the devices you had before and do whatever it is that you did before. If you'd like to learn more, please come see me at ERTech. I am scheduled to present this paper at ERTech in July. And finally, I need to point out to you that the use of GOR and total energy equivalents per day and or the breach of the energy wall signal for modifying an oil forecast is explicitly protected intellectual property under 2 U.S. patents. And please know that the integration of gas oil ratio into decline curve analysis and RTA are marketed under the trade names IGOR DCA and IGOR RTA. So please refer your preferred software vendor to Shale Specialists to have these included in their existing offerings. And with that, I'll say thank you and take some questions.
All right, thanks for the presentation, Scott. Unfortunately, we're running a little bit behind schedule, so I'm going to ask everybody to pose Mr. Scott Lapierre your questions in the chat, and Scott's right there to answer all those questions. And of course, you can follow up with him afterwards by contacting him at Shale Specialists. And I encourage everybody to go to his website if you're looking for more information and get a hold of Scott directly. Thanks a lot, Scott. And with that, we're having to quickly move on to Robert Downey. Robert Downey is the founder and CEO of Shale Ingenuity, and I'm going to put his bio up in the chat. So with
Good
that,
afternoon.
Darcy,
my name is Robert Downey. I'm president and CEO of Shale Ingenuity, Centennial, Colorado. I'd like to talk to you today about our Super EOR shale oil enhanced oil recovery process. Super EOR is a novel, superior method for shale oil EOR. Super EOR can yield incremental oil recovery of 200 to 300% above primary pressure depletion EOR, and an estimated all-in cost of about $15 a barrel. For reference, it typically costs more than $30 a barrel to recover oil on a primary basis, drilling and completions. It has multiple significant environmental benefits. It's applicable to about 80,000 horizontal shale oil wells in the United States and in Canada. They can be applied earlier in the well life to increase production, reduce the decline rate you see with these shale wells, and boost the proved reserves. It can be applied in multiple wells simultaneously on a multi-well pad, and is protected by patents. Shale Ingenuity's value proposition is to provide this technology to shale oil producers under a range of very flexible options, from contract development and sub-licensing of our patents, service model where we would come in and conduct the project ourselves and take a per barrel recovered fee. We could do farm-ins or joint ventures. Our goal is to make this technology available at a very reasonable cost so that operators can triple their reserves and production and drive their costs down, reduce their environmental footprint. Shale oil reservoirs generally are very, very low permeability and porosity and are driven, the primary energy source for driving oil to the wellbore is solution gas drive. As a result of that, you only recover about 5% of the oil in place by the time the well is pressure depleted. And that leaves 95% of the oil in place. And so this is an enormous resource that would otherwise go to waste unless some sort of enhanced oil recovery process were to be applied. This table here is from a report done by Advanced Resources International for the EIA back in May of 2013, and it shows the estimated recovery factor for a number of different shale plays here in the United States. Shale oil EOR in the United States is in its infancy. The Eagle Ford Shale probably has the most EOR projects permitted to date, 33 separate projects permitted with the Texas Railroad Commission by 9 operators. Of those, EOG is the dominant operator with 17 of those permitted projects involving 178 wells, all under natural gas huff and puff EOR. They began in 2016, and then they've since added wells each year through 2018. Their incremental recoveries have been estimated to be 30 to 70%. There's been a number of SB papers written on this that forecasted incremental recovery. However, we've also had reported problems with interwell communication, with gas traveling down fractures that communicate with offset wells, and that prevents sufficient pressure buildup, reduces oil recovery, and adds to the cost. In the Permian, there are 6 EOR projects that have been permitted by 4 different operators, and of those 4, Pioneer and Oxy's projects have not yet been implemented. In the Bakken, there's been a number of pilot scale CO2 injection tests, huff and puff tests, and most recently, Liberty Resources did a natural gas huff and puff EOR project in one well in 2019, but they had to delay it due to a lack of gas supply. Amerada Hess did a single cycle propane injection test in a well in 2019. In the Scoop Stack of Oklahoma, Continental Resources did a single cycle natural gas injection test. Unfortunately, with that well, they had communication to an offset well, and they couldn't get it pressured up after several months of injection. In the DJ and Powder River Basin, no pilots were started. Anadarko attempted an industry consortium in 2019, but that got dropped when they were acquired by Oxy. So our company was founded to deploy this advanced EOR process that we invented for shale oil reservoirs to dramatically increase oil production and reserves. We have novel shale oil, gas condensate, cyclic injection IP ownership. Our company founder is a petroleum engineer with 44 years of experience and the inventor on 22 patents. Our business model, again, is to deploy our process through licensing, joint ventures, and farm-ins. We are not a consulting firm, but we will provide technical management and operations capabilities for Super EOR project development. We have a strong, experienced team. Everybody has at least 30 years of experience in reservoir engineering, project management, facilities engineering, operations, land and regulatory, and even research. And we're also partnered with the computer modeling group. Probably has the world's best reservoir modeling software. A number of very large clients. It's just fantastic software and enables us to model our process very effectively and accurately. So some of the features of Super EOR are that, of course, much higher oil recovery than natural gas or CO2, huff and puff. We use an optimized blend of a low-cost, simple solvent. It's adjusted by cycle based on ongoing compositional reservoir simulation modeling to maximize oil recovery. This solvent blend requires a much smaller volume to pressure up. It's lower cost than natural gas, can be trucked or piped to the well pad, and is fully recoverable. You only buy it one time. It's injected into the well in a liquid state using a triplex pump. No compressors required. Uses far less horsepower to do that. You inject to a designed surface injection pressure, and the bottom hole temperature will heat the injectant and raise the bottom hole pressure. And then on the flowback, the production and the injectant are recovered in a surface equipment package where the injectant is stored on the pad for re-injection. Getting you much higher oil recovery per cycle with shorter injection cycles and a shorter overall total EOR time. The shorter cycle and higher viscosity injectant, liquid injectant, provides better control over the injectant displacement, and we can also operate this at a much lower maximum bottom hole pressure and still have excellent oil recovery, and that means much lower chance of interwell communication. The environmental benefits of Super EOR are many. First of all, at least 50% lower greenhouse gas emissions versus primary production on a per barrel of oil basis. The 75% lower water consumption in production, 75% lower capital investments, 50% lower operating expenses. Again, all-in cost per barrel is about $15. We eliminate the need for artificial lift and the energy to run it because the wells are either operated under injection or they're flowing back at all times. We have a 50% smaller surface footprint, and of course, conservation of oil resources. We're recovering, instead of 6 to 8% of the oil in place, 20 to 25% or more. Out in the field, this is how it would kind of look, a schematic. You have 16 wells arrayed on the bottom there, and then you've got a triplex pump injecting in a staggered manner into those wells, and on the flow back on a staggered basis also back through the solvent recovery unit. That allows for kind of uniform injection and production through the cycle. The solvent is recovered, stored on location for re-injection. Oil goes to the tanks, gas goes on to the midstream. I'll also point out this is very controllable, very scalable. I'll also point out that we also recover a lot of additional gas through Super EOR. I don't account for it in our economics, but it does produce a lot of additional gas that would not be otherwise recovered. Now in the Eagle Ford, we've been working with a company called EP Energy. They have 2 natural gas huff and puff EOR projects there. They also had one in the Permian, Wolfcamp. In their northern project, which is in the volatile oil part of the reservoir, they estimated their natural gas EOR recovery might be as much as 75,000 barrels per well based on their H12 filings. When they got out in the field, though, it didn't quite turn out that way, and I'll explain here in a second. This project was located in northwest LaSalle County. It was a 3-well natural gas huff and puff EOR project in the volatile oil window. This was described in several technical papers. It was modeled with CMG GEM. They got a match on primary production and pressure history. They then got a match on their natural gas huff and puff EOR performance. We use that model to forecast Super EOR performance. There's a map showing the location of these wells. Again, 3 wells, 6,400 foot lateral lengths, 25 stage frac completions. They were produced for 13 months prior to the start of the natural gas huff and puff EOR process. However, once they got going, they realized they had interwell communication, and that required them to provide pressure barriers by pumping water into the 2 outside wells and just inject into the center one. This was described in an SPE paper. The containment they conducted by pumping water into the 2 outside wells with a 3,500 PSI pressure barrier allowed them to increase their oil recovery from a 7 to 12% to 20 to 30% range. We then modeled their process with Super EOR, and this is what the result looks like, the cumulative oil versus time. So what you're seeing here is the lower curve is the forecasted recovery under primary production with a constant bottom hole pressure, and the Super EOR is the upper curve. And Super EOR is projecting a recovery of 53,000 barrels per stage versus primary EOR at 15,350 barrels per stage. So we're tripling the oil recovery by employing Super EOR in this well. We also modeled this at different maximum bottom hole pressures. The curve I showed you before was modeled at a maximum bottom hole pressure at 4,500 psi. But even dropping the pressure down to 1,500 psi or even 1,000 psi, it gets excellent oil recovery. And that's extremely important when you consider that there's a lot of wells out there that have interwell communication that they found out either through natural fractures or when they did the frac jobs when they completed the well. So by being able to operate this process at a much lower bottom hole pressure, you can effectively affect a very high oil recovery and basically operate these wells as independent reservoirs without having a loss of injectant. We also modeled the Permian Basin Wolfcamp D. The Wolfcamp is a massively thick shale in the Permian Basin. Most of the development activity is in the Wolfcamp A and B, the upper zones. The D is also called the Klein Shale, and it hasn't been developed as much. It's not as widespread across the basin. We just happened to get data, PVT data and production data on a Wolfcamp D shale well near the center of the basin and modeled it. This well had 5 years of primary production prior to Super EUR, producing 30 barrels a day. We projected primary EUR at about 123,000 barrels with an 11.5-year primary well life. We modeled the Super EUR to begin in July of 2020 and run for 500 cycles, 15 days injection, 15 days production, completely unoptimized. And we show an increased oil recovery of a little more than 1 million barrels of oil with a peak rate of 6,000 barrels a day and a recovery of 6 times primary EUR after 5 years. Pretty remarkable. And after that 500 cycles, the well is still producing more than 60 barrels a day at that period. This is another oil production graph from that same model. Just shows you on a single stage basis, their peak was about 180 barrels a day. This full well has 30 stages. And then we also modeled CO2 and natural gas huff and puff in the same well to see how they would compare. And you can see CO2 gets you another 40%, versus 600% increase with Super EUR in this particular well. We have also conducted core testing on Eagle Ford and Permian Wolfcamp shale cores to confirm the physics of the process, determine how it would work. I can report that after conducting these tests, which were 6 cycles of solvent injection and flowback, we recovered more than 90% of the oil out of these cores. It's remarkable how effective this solvent is at pulling the oil out of these shales. It truly is. What do the economics look like? Well, here's an example from the Eagle Ford where we modeled a 16-well Super EUR project. We assumed a $40 oil price with a $5 basis differential. Process, again, was just unoptimized. We assumed injection and production time. The project economics were based on 10 years of operation, although I will tell you this process is still very economical after 10 years. But for financial reasons, we just decided to cut it at 10 years. And you can see the rate of return is over 100%, ROI is in excess of 4, and the cost per barrel of oil recovered is about $13. So it's remarkable economics. We think this would be something that should be of great interest to the shale oil industry. That's a great way to drive the cost down, reduce your greenhouse gas emissions, and triple your oil recovery. We have patents covering this. As I mentioned earlier, we have 2 patents and some additional patents and trademarks pending. We have issued patents broadly covering cyclic natural gas EUR in shale oil and shale gas condensate reservoirs, and additional patents pending both at USPTO and WIPO. We have a contingency agreement in place with our IP counsel to protect our IP ownership and to prosecute infringement of our patents. We hope that doesn't happen, because we're going to try to license our patents broadly and under very reasonable terms so that we can enable shale oil producers to access this technology and to their benefit, and at the same time discourage infringement. So how would this work, deploying this in the field? Well, first it starts with executing a mutual confidential and non-compete agreement with us so that we can share confidential information. We then select representative well or wells to evaluate for Super EUR. We basically build a compositional reservoir simulation model using PVT, well completion, geological production, and pressure data. get a history match on the pressure and production data, and then model the super EOR process to forecast oil production, and even then run the economics based on your production forecast. Once that's done, we could then model and conduct a single well field test of the process. We would design the field test to validate the simulation model projections, estimate the costs, conduct the test, and evaluate the results. And once that's done, if the operator wants to pursue development, we negotiate an agreement to access the technology. It would be a sublicense of our patents. And we can also utilize those field test results and data to model that project for the operator. We would design, install, and operate the super EOR project either for the operator or with the operator, however they would like to proceed. So just to summarize, we've developed a superior method for shale EOR. It's simple, it's very effective, it works very well, it can be deployed very easily in the field. It generates a great recovery of oil in the first 5 years. All-in cost $15 a barrel, has multiple environmental benefits. It's applicable to more than 80,000 horizontal shale oil wells across the U.S. Can be applied earlier in the well life to increase the production, reduce the decline rate, and boost proved reserves. It can be applied in multiple wells simultaneously on a multi-well pad, and it's protected by patents. And we can offer this technology on a variety of options for shale oil producers to access this technology: contract development, sub-licensing, service model, or farm-ins and joint ventures. We think this is game-changing technology. We think it can really help the oil industry with this, drive the costs down, make us more competitive on the world stage, help the economics for operators to operate their assets, and then also drive down the environmental impacts of shale oil development, which is very important. Thank you for the opportunity to tell you a little bit about super EOR and Shale Ingenuity.
All right. Thanks a lot, Robert. So with that, I'm going to sign off and say thank you very much for joining our webinar series. And this glorious Viking behind me, Darcy Fairbrother, is responsible for everything that you saw here with Demio and uploading all the videos and launching all the polls and chats. So thanks to my co-founder, Darcy Fairbrother. Look forward to seeing you in our next webinar series, and hopefully we look forward to seeing you at our conference as well. If you've got questions about subscription for our digital platform for online training and education, you know where to find us. Thank you very much.